My name is Dave Hansen. I am a kernel engineer. I want to talk to you here about managing new memory tiers. I feel like working in memory, it's none of those things that people from the outside look at it and say, man, how hard could this be? Because I look at something like power management and I'm like, how hard is power management? It just make the battery last longer, or core scheduling. It's like, just make things run, and how hard is it to schedule stuff on a CPU core? Just run the tasks. I want to convince you today that memory is hard and memory is complicated. So let's get into it. I feel like there have been a couple different eras of memory in computing. The first era I call memory is memory. You look at a motherboard, you've got some memory slots there, you got a CPU there, and all the memory is the same. There's really no difference between any of those memory slots to the CPU. All memory is the same, memory is just memory. It's boring. The second era is called NUMA. And NUMA machines started to be built kind of in the 90s. Companies like SGI and Digital started making machines where there were bunches of memory and bunches of CPUs, and some CPUs were close to some memory, and some CPUs were far from that memory. And so this took a long time for operating systems to get kind of enabled to do this, because for a long time operating systems had just said, memory is memory, I'm going to manage it, it's flat, and all of a sudden they had this concept of near memory and far memory. So that's the second era of memory. And the reason that you would want to do near or far is for performance. The stuff that was near is faster, the stuff that's farther away is slower, and you want to make sure that when you're doing calculations on a CPU that the memory that you're operating on is close to the CPU where you're doing the work. So where do we go from here? Well, traditionally, we've just had normal old memory DIMMs, and pretty much every DIMM in the system is the same. But now we've got these snazzy new things like our new persistent memory products, and all of a sudden you can have two DIMM sockets in a system. One of the DIMM sockets is regular old DRAM. It's fast, close to the CPU. But there's another DIMM right next to it, and it looks really, really similar to your regular DRAM DIMM, but it's persistent memory. And it turns out the persistent memory is great. The capacities are really, really high. But it turns out that some of its media properties are a little bit different. It acts a little more like flash than RAM. And so it's a little slower to do some operations than normal RAM would have been. And so this has gotten a little more complicated because we have the concept of NUMA here as well. We have near and far, because you can still plug these DIMMs in anywhere in the system. But all of a sudden, in addition to just being near and far, we have two types of memory. We got fast memory and slow memory. Well, there's something else here too. Intel has an earlier product called the Xeon Phi. These were really, really cool little systems. They also had DIMMs on them, regular old DDR memory, and it was sitting attached to the CPU die like everything else, or attached off the CPU die like everything else is, regular old DIMMs. But it also has the other little things, and you'll see that there are these little purple packages here that are labeled MCDRAM. This stuff is really cool because it's on the CPU package. And it turns out that this stuff is really high bandwidth, and you can use new CPU instructions to do really, really fast calculations on this memory. But there isn't very much of it. I think you can fit tens or dozens of gigabytes of DDR in these systems, but there's only about 16 gigabytes of this stuff. And so all of a sudden you had to start to make decisions about, well, what am I operating on here? Am I going to be doing these vector operations on this data, and I need it in this special high bandwidth memory? Or am I going to be doing normal old operations on it, and it can sit out in DDR, just like normal old memory? So things are starting to get a little more complicated here. We've got three different types. So, and here's how that looks back in the same diagram we saw. Notice that this looks the same as the other system that we just had, the NUMA system. From the outside, it looks the same, but we've added the fast memory, and it's sitting inside the CPU package. We still have the DRAM there, and it's slower, but still, we have a system from the outside that looks exactly the same, but we've added another kind of memory that we have to deal with. Turns out that there are also RAM types getting added other places in the system. So GPUs have memory, and turns out FPGAs have memory, and so people want to plug these things in. Traditionally, these things have been sitting off, and a device driver would move the data in and out of the memory on the device versus the memory that was in your RAM, for instance. But with the CXL technology that's coming around, that memory, from the processor's perspective, is now cache coherent. And that's really, really important because it means that all of a sudden, normal applications can access it. It has all the same rules that regular RAM does in terms of how you can give it to an application and how you can manage it. And so the management is moving more and more into the core OS for these things. These devices haven't showed up yet, but this is just an example of where we expect this stuff to go. So let's kind of lay all these things out together and see how our system starts to look. We have our memory on our FPGA. We have our fast, high bandwidth memory sitting on the processor. We have our kind of slow memory. We have our DDR that's sitting out in a DRAM slot somewhere. And then we have really slow memory, like persistent memory. So what do we get when we add all these things up together? I think these all add up to a new era of computing, and we're calling this heterogeneous memory, or additional memory tiers. So why are people doing this? Like, as I said, things are getting way more complicated. It used to be one type of memory, and now we've got a bunch in the system. So what's happening here? Why are people doing this? Well, this helps you maximize CPU utilization. One thing that Raja said yesterday is that memory bandwidth isn't going up. And so the processor actually can't use its full capabilities. The processor is bottlenecked on data being fed into the processor. And so that's the reason that these things were added, like this high bandwidth memory, is to basically allow the data to be closer to the CPU and keep that CPU core busy and happily churning away with its new fancy vector instructions. The other thing is for things like persistent memory. Persistent memory is great. You can store data on it. It can be used in the same way that like a flash device would be used to have a file system and store files. But it turns out that a lot of times you have to modify your applications in order to use this new technology. And people have asked that instead of using this new persistent memory for its great persistence capabilities, that instead you use it just as storage, just like you would use RAM. So people want to use it to expand the DRAM they have on their system, either to replace other DRAM that they would have bought in the system or to expand the capacity that they already have. This also allows you to dial in performance. So since persistent memory has lower performance in general than DRAM, you can build a system and you can say, hey, I'd like to choose the cost that I'm charging my customers. This is the bronze, silver, gold model. So maybe I'm a cloud provider, and I want to provide a large mix of systems to my customers. I want to provide some that are very expensive and faster, and I want to provide some that are kind of middle of the road, and some that are slower and cheaper. And customers love this stuff, right? I mean, this is how Intel sells its CPUs. We've got large core counts, so we call those the platinum systems, and they've got lots of features. And there are also different parts that have a lower price point, and customers like to be able to make these trade-offs. So this gives people the ability to build products where you've dialed in your performance here, and you can charge your customers various amounts based on the performance they're going to get. And also, once you have these memory on devices, like I showed on that CXL device, there's a reason that people do this. And the reason is that you want the memory that you're going to be operating on to store the data that's going to be close to the processor doing the processing. And for an FPGA, you want some RAM sitting on the FPGA. If that's a graphics card, you want the memory and the data that it's going to be drawing to the screen or doing its fancy AI calculations on close to the processor that's doing the processing. So once we can make the operating system understand all these types of memory, and we can make sure that the operating system understands where to put things when and who's going to be operating on it, we can build these faster systems and also build more customization and more solutions that people can sell. But here's the problem. Right now, we're still living in that second era of memory. We have all these memory types exist today. Persistent memory, I believe you can go out and buy it. I'm not quite sure if you could go out and buy it on Newegg, but it's getting close. I really hope. And so you can go buy a server today, a 2-socket server, and that's what I've shown on the deck here. And that server will actually show up, and it will appear, if you plug some persistent memory into it, it'll appear to the operating system to have 4 NUMA nodes. And so traditionally, these NUMA nodes have kind of meant a socket. But we've redefined that right now to kind of say, well, in addition to a NUMA node meaning a socket, it can also mean a type of memory. And so it means kind of a particular type of memory attached to a particular CPU. But this is a little unfortunate because, as I said, these things have different properties now. We have persistent memory that has differing read and write speeds, for instance. It takes longer to write to this stuff than it does to read. But the only thing that we have in our firmware today is a distance. This firmware was developed about 15 years ago, and it was developed for those simple NUMA systems where memory is either near or far. And so for those systems, what we had is a table that says how near or far it is. And in this table, you can see like a 10 it means as close as possible. And things that are a little farther away, we can see the persistent memory attached to the same processor. It gets a 17, so it's a little farther away. And the DRAM on the next socket gets a 21, meaning it's a little farther away. But this is a really flat thing. And also, look at this number. It's just a 10. There isn't even a unit on this. Like, what is this? So the ACPI spec talks about this being a latency number, but what is it? I mean, is it nanoseconds of latency, or what is this thing? It doesn't even really have a unit. There's also a little problem with this stuff in that people have started to camouflage memory in systems. Like I said, there was that high bandwidth memory on our Knights Landing processors. And that stuff's expensive, and there's not very much of it on the system. And so people were using this distance information to say this is expensive. And the way they were doing that is saying it's really, really slow. So even though it's the fastest memory in the system, if you went and looked at the firmware table, it would be disguised as the slowest memory in the system. And this was to make it unattractive to things like the kernel, to make sure that nobody put any data into it. So, and the other thing is that people would take systems like this and they'd say, I'm building a new BIOS and I've got to fill this table out for my system. What number should I put in here? And so they used a very data-driven approach. And they would put some numbers in this table and they'd run a benchmark. And they'd see what the benchmark was, and they'd put some other numbers in the table and they'd run the benchmark again. And whichever one got the better information, or got the better benchmark results, that's what they would publish in their product. And so this happened over and over again. So this is what happens when you have a table that doesn't have any units. It's kind of this nebulous thing, and people can basically, if you're a BIOS vendor, you can put whatever numbers in here that you want, and the OS will just kind of use those numbers and assume it's a legitimate, valid distance. And well, we get some kind of crazy tables out there. So this is problematic. It doesn't describe what we need, and it's easily it can be easily manipulated in ways that us in the OS don't really like. What we want is really the truth. We want the hardware and the firmware to describe to us what's there. We don't want the firmware kind of trying to dictate OS behavior with some other, some crazy numbers. So here's our solution. One of the newer ACPI specs has this new table called the ACPI HMAT, and this is designed to fix all those problems I just talked about. So I'll walk you through a couple of things that are pretty cool about this. You'll see that there's a lot more information in here. Previously, look at this table. There's nothing in here, just some raw numbers. So the first thing that we get are things like actual performance numbers. And there's some argument as to whether these should be things that you actually saw on a benchmark or just like the sticker speed of the bus. And so these probably aren't the numbers you'll actually see if you ran a benchmark on these, but they're close. And these are what the firmware will provide to us today. And you'll notice that we actually have units on this now. We actually have nanoseconds. And it's a lot easier to say, hey, you got this value right or you got this value wrong when it's a unit that you can say instead of just some nebulous number like a 10. So let me just point out also, these are entirely made up. I put all these in here just guessing what the numbers would be. This isn't an actual table from any kind of real hardware. So it all came out of my head. So notice also that we get separate latency and bandwidth numbers for read and write. Traditionally, this isn't a big problem for things like DRAM, but for these new technologies like persistent memory, the read and write bandwidth can be very, very different because the new persistent memory acts a lot like flash in terms of writes are a lot slower than reads. So it's really, really important to have this information, and this can't be reflected in that single number, that single distance number. It just doesn't make any logical sense. So what this table gives us is separate read and write latency and bandwidth, and it also has the ability to tell us where the processors are actually attached. This was a problem previously because, like with that MCDRAM example, you didn't really know where the processors were. Each one of these NUMA nodes will either have the processors or not, but this lets you know this also lets you say where the allocation should go first. The processors, the way the kernel tends to work is that we try to allocate memory as close to the processors as possible. And in general, that's meant give me the fastest memory that you can. But we've seen in things like that Knights Landing example that we don't want the fastest, most expensive memory to get used first. So this new table also allows us to say, to essentially express the intent for the system builders where they want memory allocations to occur first. The kernel isn't really bound by this. We can do whatever we want in the end. But this at least lets the people who are building systems express some of that intent instead of trying to like fudge the tables to get that behavior after the fact. This really allows them to express reality of what they want instead of trying to reverse engineer how the OS works. And you'll also see here that in addition to saying what's closest to the processors, we'll actually tell you for every kind of memory which processors it's attached to. So this is really handy if you want to know, hey, is this stuff given, like if I want to go find the persistent memory that's the fastest for a given CPU, I want to go to the stuff that's attached to me. And so this actually tells you the physical attachment of things. And before, with that distance number, you kind of might know what was the closest, but you don't really know what the attachment is. And so this makes it really explicit which memory is sitting where and how the system is actually laid out, which is really what us OS designers want, is we really just want the system described to us fully instead of us trying to have to kind of parse it out from some halfway information that we had previously. And also, we added a little bit that is called the reserved bit. I think this got moved somewhere else in later versions of the table. But this is somewhere in the firmware, I promise. I don't remember where it is today, but it's still there. But this is a really cool thing because this fixes the problem also with that high bandwidth memory, where people wanted it to be there, described, and described as being really fast, but also they don't want the OS to go and use it. This stuff, to be honest, the kernel wouldn't know what to do with this stuff. The kernel can barely even execute the instructions that it needs to run at full speed on this stuff. The kernel is barely even allowed to execute those instructions. And so what this allows us to do is to say, hey, kernel, leave your grubby mitts for your silly kernel data structures out of this really, really fast memory. And so it's reserved from the OS. And again, the kernel doesn't have to respect any of this, but this at least says, hey, kernel, please leave this alone. Please leave this there just for my applications. And so this allows us to build things where the kernel will boot up and say, hey, this stuff is reserved. I'm going to leave it alone and leave it for these very specialized applications that really know how to take advantage of this stuff. And so this will keep the kernel out of the business of stealing this fast, expensive memory. So I can talk a little bit about where this is leading us. So we actually finally have support in the mainline kernel for this new table. I believe it's queued up for the 5.2 kernel. But one thing that happened is because we decided to repurpose our old NUMA infrastructure, it turns out that if you took a system that has this heterogeneous memory on it, plugged in persistent memory, and you had one of these coherent devices, and you had high bandwidth memory, not that any system actually has that today, but if you took one of those and put it in an old kernel, and this is 5.1 and earlier, you would just get a bunch of NUMA nodes. You wouldn't have a great description of how fast they are or what they're supposed to do, but you would have a description of those NUMA nodes. And so even on an old kernel, you at least have the ability to allocate memory to a given NUMA node and to a given memory type. You could boot up on a system and say, hey, I want to use just persistent memory for my application. And you could use the NUMA APIs if you knew which NUMA nodes were what. Even on a super old kernel, you could still say, I want to build my app and I want to use just persistent memory, even though that kernel has absolutely no knowledge of persistent memory. And it also has no knowledge of these new tables. So that's pretty cool. It was a nice kind of fallout from the way that we inherited the old NUMA infrastructure in the firmware. But the discovery that's been added is essentially taking that table that I talked about, and we can parse it all now. So we have the ability to take all that information and consume it and pull it into the kernel and at least express that out to applications. So all those latency and bandwidth and the reserved bit and all that stuff is sitting there and can be read by applications out in our sysfs directories. So you can, right now you can take an app, you can spool it up and go read the information in sysfs to figure out exactly what the properties of all this memory is on your system and make sure that your applications can be optimized properly. Also, at the same time that stuff shows up, we should have the ability to reserve it, like I talked about, to make sure that that the kernel will keep its data structures out of the expensive specialized memory that we don't want it to actually use or access. But this actually leads us to a little bit of a problem, which is that the kernel now can understand this stuff, it can reserve it, but we're kind of left with a kernel that doesn't really know what to do with this new memory. And so the next push now that we have kind of the basic infrastructure in place is for the kernel to really truly be able to optimize apps that are sitting with this stuff. And so like persistent memory, one really great thing we can do with it is that it's kind of a new tier in between regular RAM and, for instance, the swap or the I/O that's sitting out there. And so what we like to be able to do to optimize applications is say, instead of, like right now, if you ran out of DRAM on a system, all of a sudden the kernel would start throwing some of that data away. And if you need that data again, you have to go back out to the disk to get it. The disks are really slow. So essentially what would happen is we skip right over that persistent memory tier. Even though persistent memory is slower than DRAM and faster than the disk, the kernel has no idea how to use it. And so as we look at optimizations, what we really want to make sure the kernel does is is it starts to use that persistent memory tier. So if we run out of DRAM, we'd like the kernel to take that memory and shove it off into persistent memory so it can be kind of cached there temporarily in case somebody needs it again, because it's a heck of a lot quicker to get it out of persistent memory back into DRAM than it would be to go out to a disk or even an SSD. So there are a ton of things that we can do in the kernel to make sure that we've taught the memory management mechanisms how to understand that now we have multiple pieces of memory that a piece of data can progress through as it ages and eventually may end up out on the disk, but also might get brought back into the faster memory tiers. So there's a lot of work there to tie in this new tiering into the memory management subsystem. Memory management is a very conservative and slow-moving area of the kernel, so we expect this to take a long, long time to get right. But there's going to be a lot of work there to make sure that this new tier is fully utilized and that the kernel really natively understands what to do. And using the very scientific timing, we expect optimizations to be happening soon. There's certainly lots of patches out there, lots of ideas about what we can do. Lots of things like I said, with persistent memory, it has slower write performance. So maybe if we know that we're going to write to the memory, we'll pull that into DRAM and get it out of persistent memory. So there's a ton of ideas here, and we have no idea which ones are going to work out. So there's going to be a lot of experimentation, a lot of patches, and a lot of benchmarking that's going to have to happen before we can move this along. But this is an exciting thing, and there's a lot of different ideas for things that we can do here. So this stuff will only grow over time. Our NUMA support, for instance, started out 15 or 20 years ago, and it really didn't do anything. We added things to it over time where we added applications could move memory around, and we added an auto NUMA daemon that can go around and figure out which memory is being touched and migrate it to new nodes automatically. So we expect that same kind of stuff to happen. This will be stuff that evolves, and the kernel will slowly grow the capabilities to make sure that these multi-tiered systems are optimized and hopefully transparently work without applications having to actually understand all the complexity of all these tiers underneath. The other thing that happens is that since we have all these different kinds of memory in the system, and if you want to start building a system where you have that bronze, silver, gold model, right now you can kind of build that. You can sit out there and try and manage these applications from the outside. But we really want to add native kernel support for these things, where you can say, hey, I want to give this particular application maybe a 50-50 split of slow and fast memory, or this application an 80-20 split. So there's going to be a lot of work to make sure that we have limits and quotas and essentially C-group support for these kinds of things, because people are going to want to build these differentiated services out of these tiers of memory. So we expect a lot of work to happen there, not soon, but this we expect to happen a little bit later once the rest of the kernel kind of starts to understand how these things work. So please come help us here. As you can see, there's lots of hardware being built with this stuff. People are putting persistent memory in systems and using it in weird ways. Once these CXL devices start showing up, we're going to have hopefully people crawling out of the woodwork making devices with RAM on them. And the OS is going to have no idea what to do with them. So we want to know, from the kernel community side, we want to know what hardware you're building with this, what you're putting in those tables, what you want the kernel to do. So please feel free to reach out to people if you're building hardware that's doing this, or you know of weird hardware that the kernel doesn't comprehend. We also want to know what customers want to do with this. Largely, Intel makes the hardware, and we ship it off to the customers, and they do magic with it. But sometimes we miss that communication feedback loop, and we don't actually understand how it gets used or what problems people face. So we would love to hear early when people see these systems, what they want to do with them, what kind of solutions they want to build with it. So please let us know. There are constant trees being updated with those new experiments and different things going on. Here's some of the GitHub tags that we use to store these things as we are experimenting with them. This isn't the super stable set of things. It's really the set of optimizations kind of today that we're playing with in benchmarking. But it's a good place to kind of see what activity is going on and what we're doing in the space. And all the discussions here are happening out in the open. Now that this ACPI table is public and most of the hardware that we're talking about here is public, all of our discussions are happening out in the open, and they're happening on the standard memory management mailing list.